So my name is Mialancho. I'm a software engineer at Zidida, and in this webinar, I'll be talking about mostly about networking, but I will also mention the hardware model, which was specifically requested. So this is the session part 4. There are 3 other parts available on this link that you can see. In this one, I will be talking firstly about the hardware model description files. Then I will be talking about networking, and there are several categories or several topics like device connectivity, application adapters, network ACLs. I have some examples and live demonstrations prepared, and I will talk about network troubleshooting and some best practices. Okay, so the hardware model. So the hardware model in Eve is represented by a JSON file, which describes essentially for a particular device, it describes all available hardware resources available for you and or for applications. And this is needed both for EOS as well as the controller to know what resources are available, which of them can be allocated for the host, for the EOS, and which can be allocated for applications. So the hardware model, as I mentioned, is a JSON file which contains a description of available hardware resources. So there is some general description which should include a link to device photos, ideally front and back. This is because on the device enclosure, you may have some printed labels next to input-output ports, like network interfaces, for example. And it is good practice to put these physical labels into the model so that one can, see a particular input-output record in the device model to which hardware port belongs to. And also there should be, or it is recommended to put the URL from which the device can be purchased. And more importantly, it should contain attributes for CPU. So that means how many CPU cores are available, how much memory is available on that particular device, what storage is available, attributes for the trusted platform module, and so on. And then finally, the most of the model is actually a list of input-output adapters like network adapters, serial consoles, or VGA ports, and so on. Now, these adapters, there are some limitations due to hardware limitations. They cannot be they cannot be separated from each other always, and this is because there are some constraints. For example, a group of adapters can share the same DMA controller, and it would be insecure to separate them, to put them into different applications, because for example, it could be possible in theory for one application to use this DMA controller to read physical memory from another application. So there are some constraints of how we can assign these adapters and how we can split them from each other. And these are in Linux covered by EO MMU groups. And so if 2 adapters are in the same group, that means that they cannot be separated from one another. And in the Eve model, this is covered by the assign GRP field. So if 2 adapters, or if a group of adapters is in the same group and cannot be separated from each other, then it should have the same assign GRP field value. And let's say that one of these devices is actually needed by the host, by EOS. In that case, the other adapters in the same group cannot be put into application. They have to stay together, and they have to stay in the stay for the host, to be used by the host. And in that case, the assign GRP should be set to empty string. So that basically means that not usable by applications. And then We have some model files already prepared for a set of devices which are commonly used with EOS, and we have them in the Eden repository. So LFH organization on GitHub, Eden repository, and directory models. And so you may find a model for your device already there. But if it's not there, then you need to prepare a model file by yourself. And you can get started using this script here mentioned in the Eve repository and subdirectory package debug, and the script name is spec.sh. So this script can, to some degree, generate this hardware model. It can detect how many CPU cores are available, how much memory is available. It can also list the input-output adapters. It can get this information from the /sys file system, and also using the tools like LSPCI, LSHVA, LSUSB.
Milan, just a quick question. Are we uniquely identifying the model files, right? What do you have any mechanism in place to uniquely identify the model files?
I don't think so. They have like the file name is unique, at least in this database. But actually, I'm not sure.
So, is your question about how you actually name the models afterwards?
No, I'm just thinking of, it's possible that, for example, we go to the portal here, and let's say there are 3 model files that claim to support the device. How do we know whether there's not an overlap, or one is just not a slightly different permutation of another one? Like, what guarantee do we have that when we see a model file for a device, that model is truly supporting that device?
Yeah, I don't think you can tell that. I mean, some of the hardware vendors, right? What we could tell, which we actually, I believe the script doesn't extract today, is there's a utility DMID code which extracts things from the BIOS, which is telling me what the vendor is, what their notion of model is, etc. Right? But we've seen plenty of cases with some vendors where they have lots of variant strings for these things that don't necessarily differ that much, right? But they just, because they're sort of doing this stuff through OEMs and SIs, they crank out new names for different hardware left and right. So it actually does require some amount of, if you have a new model that you're getting from a vendor, sort of figuring out, okay, does this already exist in the set of things that are living in Eden/models, right? Yeah, that requires some manual work. And it's also, if it doesn't exist or not, you still need to do some testing to make sure that all of the stuff actually works as advertised. Right? The hardware model.md file actually talks about some of the testing that's needed, but the sort of naming of these things, yeah, not something that is easy today because of the way the hardware manufacturers crank things out.
Yep. And Obi, I would like to add that on top of that, if there is a manufacturer that is going to say that a certain device or a certain model corresponds to a certain device in its current configuration, then that is exactly what it means, right? If you have a slightly different variation of the device, then the model will change or might change depending on what those variations are. So if you see that there are 3 different hardware models are listed there, then that is because they are 3 different variations of that same device. So at some point, like, we will have to go back a little bit more deeper to figure out which exact model you have, hardware device you have, and which one corresponds to that.
And in some cases, the things that we've seen is like, yeah, there's one that potentially could have an LTE modem. Is there an LTE modem or not, right? That's an example of 2 different variants. And yeah, how do you tell which one you have, right?
So pretty much the summary is basically, we if we're putting up a new device, we better just make sure the model is generated properly, right? So we can't really blindly trust the models that are in Eden/models. We have to, I guess, do it ourselves and verify it ourselves, right?
Yeah.
I mean, I think like that is one extreme. Like I would say, like the models that are there in Eden are first of all going to tell you two things. First one is it's a good starting point for you, so you don't have to reinvent everything. The second thing is like it also tells you that like, hey, these models exist. These models have been played with once. So it's not just about saying that, hey, a model exists and that this is the description of the model, but you also want to make sure that the correct drivers are there and the correct drivers are present within Eve and they are working as they should be working, right? So that also becomes, that is the second step. And in my mind, like that is the harder and much more important step because that cannot be scripted. So spec.sh will give you a good version of the model, but afterwards, like there is still a much bigger task of like making sure all the drivers and everything else that are required are working in a proper way.
Thanks. Thank you.
Yeah, thanks for the question. Yeah, as Eric mentioned, once you have this model generated, you still have to test it. You still have to verify it that it actually works. This MD file here lists all the tests that should be done. Like you should maybe try to assign each adapter and then test that it's still working, and then the other adapters are still working. So there is manual work is needed definitely. And then I have a small demo prepared because I have a. So I will be showing also the ZDDA commercial controller. I have a device running actually here on this computer. It's a virtual machine, so it's a basically, it's a custom hardware emulated configuration. So it's nothing like any other models that we have, obviously. So I needed to prepare my own model, and I did that basically, using any text editor, and then in order to import it, I use ZCLI. So what I did is I run a container ZDDA ZCLI, and then I mount the models directory in which there is already a model that I have prepared for my virtualized machine. And I can actually show you my model. It's a very simple one, just for this example. So in my case, we already had a model for like a virtual machine, essentially, that we use often for testing purposes. But I have here also a LTE modem on a USB port. So I needed my custom model. And as you can see, so I have two Ethernet interfaces in separate assigned groups, so they can be assigned separately. And I have a LTE modem connected through USB. And let's say that there are some other USB ports. It may be the case that they are like under one IOMMU group. And in that case, basically, the LTE modem could, in some cases have the same group as other USB ports. And in that means that they have to be assigned as one group. Okay, so this is my model. I'm not committing this, to a repository. I'm just using it for this demo. And in order to submit it, I will just copy here the command which is necessary. So you use ZCLI model create. You will give it some name, some descriptive name. Here is the path to the model file, and then the brand. Well, in this case, it's a virtual device, so this is like a fake brand. Now I'm already using this, so if I run this, it will tell me that it already exists, but otherwise it would be added into the marketplace. And if I go back to the Z control, and if I would go to marketplace, I could find it. I have already here opened, so it's this one. This is my model as shown by the Z control. So in summary, when you are submitting a new model, you use ZCLI, but you can then view it through the Z control UI. And here I can see all my adapters. Okay, right. So this was for the hardware models. If there are any questions, feel free to ask anytime. Next, I will be talking about networking for the rest of this webinar. So firstly, I would like to clarify some terminology, which may be confusing, because sometimes we talk about networks and other times we talk about network instances, and these are two different things in EOS. So by network, we usually mean edge node network, and that's basically a connectivity between an edge node and the controller. So it is basically a network to which a device is connected through a physical network adapter in order to either provide a connectivity with the controller, or actually it can be port to some other external networks for applications to be used by applications. And these networks obviously can be of different types. So you may have Ethernet interfaces, or you may have an LTE modem, or satellite connectivity, or Wi-Fi. However, there are some challenges. For example, these physical networks, they tend to be, especially if you have like a device in some remote location, then the networks may be unreliable. And for that reason, you implement some mechanisms to deal with these problems. So obviously, if physically it's not possible for a device to have connectivity with the controller, then there is nothing that OVS can do in software. But if you have multiple interfaces that can potentially provide you connectivity with the controller, that's what we call redundancy. EOS does support it, and it can test all these management interfaces and choose the one which is actually working. So it has the mechanism of failover. It can switch from one management interface to another if the one which is being used stops working. And also, I will talk about the mechanism of fallback. If you put a wrong configuration, which would basically break connectivity, then the EOS is able to fall back to a previously working configuration, thus preventing from device losing connectivity with the controller. Another challenge is that some of these connections may be metered, so not really very costly, or not free, definitely. And for that, we allow to assign costs to network adapters. Basically, then the algorithm which tries to choose the management interface then tries to, obviously it always tries to keep the connectivity, but also it tries to optimize the cost. So it will use whatever interface is working and has the lowest cost. And then in a situation where you fail over to some other interface because the primary one stopped working, let's say you switched from Ethernet to LTE, you may configure download limits for that particular connectivity, so that in that failover period, the EOS will not be downloading large files like application images, for example. Another challenge here is that it's insecure. It goes through devices where you cannot ensure security. And for that reason, the traffic between the EOS, between the edge node and the controller is encrypted. The edge node has to authenticate itself. And also there is an option to configure a proxy. So if you have some, for example, some content policy that something is not allowed to go through, then you can put a proxy in between. And then, so this is the edge node network, right? And when we are talking about network instances, we are actually talking about virtual switches, which are inside the edge node, managed by the EOS. So EOS is management plane, and Linux network stack is the data plane. And these virtual switches are there to provide networking for applications. So these network instances provide connectivity between applications on the same node, between themselves, but also between applications and external endpoints. And so there is some overlap, between network instances and networks, because if you need external connectivity, then the network instances have to be somehow connected with the edge node networks. And also so there are multiple types of network instances, and for some of them, I will talk about it in more detail. EOS provides various network services like IP address management, DHCP, DNS, and it also logs all the flows for debugging purposes, for example. And as I mentioned, there is some overlap, and Actually, network instances may either have their own dedicated uplinks to provide external connectivity for applications, but they also may use the same ports which are used by the management plane. So there can be, the uplink can be used by both applications and EOS. So this is basically an overview in picture. So on the top you can see there are some example applications. In the middle there is the EOS. There are some examples of network adapters or input-output adapters, but let's focus on the network adapters only in this case. So there is a local network instance. I will describe this in more detail in a minute. And there is another network instance. So there are like two virtual switches running inside the device. And they provide connectivity between applications, but also between application and external endpoints. So there is an association between a network instance and a physical network adapter. Now let's focus on this part, on this bottom part, on the device connectivity. So that's connectivity between EOS or device in general and the controller. So the goal is to provide eventual connectivity, because not always the connectivity is possible, even in physical terms. But you know, if it is possible to provide connectivity through any one of the physical adapters, then the EOS will try to use that and reach this goal of having connectivity. Because if you lose connectivity forever, then the device becomes unmanageable permanently. And the connectivity can be lost either for some physical reasons, because as you know, the networks are unreliable. Some of these adapters may lose connectivity, but also it can be lost because of bad config. If you submit a configuration which is incorrect, if you by mistake if you select a network adapter as a management port by mistake, like one that is not actually providing connectivity to the controller, then what would happen is normally is that the device would lose connectivity with the controller. But there is a mechanism. EOS manages a list of network configurations, which is prioritized. It always maintains the latest received configuration from the controller. So that's like the intended state, not necessarily the working configuration. Then it also maintains the last working configuration, so the one which was proven to provide connectivity with controller. And then there are two more which are used often at the beginning, after the first boot, before device connects to the controller for the very first time. So there is an optional last resort. So basically, if you don't put and then there is also an override. You can put the first network configuration you can put through a USB stick. But if you don't provide that, then the EOS will use so-called last resort, which is basically to try every Ethernet interface, assume that there is a DHCP, try to obtain IP address, and try to connect to the controller. So this is what should provide the first connectivity with the controller, and then it will try to receive the actual intended configuration. So as I mentioned, you can override this, and then it will be configured by the controller. And in case you put there a bad configuration or the one which is not currently working, it will fall back to the last working configuration. But at the same time, it will be periodically retesting the latest configuration, because that's still the highest priority. And the moment it starts to work, it will switch to this highest priority latest configuration. So there is this periodic testing mechanism with fallback. And it's very important that you do not configure interface as management if it cannot physically provide connectivity to the controller, because otherwise it will be basically slowing down this periodic testing process. And a bit more detail about the management ports. So these are the network adapters which you mark as for management to be used by EOS to connect to the controller. As I mentioned, you can put a cost to them. Zero cost basically means that they are free essentially. So that will be typically used for Ethernet ports. And then you put higher costs to some, like a failover connectivity options like an LTE, for example. And EVOS basically, as I mentioned, it runs this algorithm when it tries to use the management port, which is working and has the lowest cost. And there can be actually multiple management ports, like you can have multiple Ethernet interfaces or zero cost, and all of them are working. And in this case, it will even run what we call load spreading. So it will be sending requests evenly between them. So it will be using them evenly. And for these management ports, as I mentioned, so they are periodically tested. So we have all this information if we have the connectivity, and all this information, including metrics, is reported by EOS to the controller. And the commercial data controller highlights management ports which are in a failing state, like can be seen in this screenshot. So this is a screenshot of some device. There are multiple network adapters, and this Ethernet 0 is marked with red background. And there is some error description, basically meaning that this management interface currently isn't providing connectivity with the controller. I have actually a demo prepared, which is in this case pre-recorded. So this is my device. This is my virtual device, but it doesn't really matter. And I have 3 adapters. As you can see, the Ethernet 0 is marked as management. Ethernet 1 isn't, because it physically cannot provide connectivity controller. And there I have a LTE modem, which can be used if Ethernet 0 doesn't work, but otherwise it shouldn't really be used because it's costly. So I put a higher cost here. It doesn't really matter what value I chose. It's only important that it's higher than whatever is in Ethernet 0. Now, here you can see that there's an IP address. Nothing is marked, highlighted with the red color. Everything is working. And we will simulate basically a network connectivity outage for Ethernet 0. Here I just use some IP tables. It's just a trick to simulate a network connectivity loss. Here I have a console connected to the device. So if you have a serial console connected to the device, you can see this output, which is informing you about connectivity. Here you can see that it detected that only 1 out of 2 ports specified to have EV controller connectivity passed test. That's because the Ethernet 0 stopped working. So there will be like an error mentioned here. Eventually, this will appear in the Z controller as well. Like I have cut out some frames. This takes like 1 or 2 minutes to detect and to be reported to the controller. And here we can see the error.
I think it might even take longer, right? Some of these tests run like every 5 minutes, I believe, by default. So it can take 5-10 minutes before it realizes that it needs to switch over.
Yeah. But here you can see the device is still, shown as online. We still are getting all the updates, and that's because it failed over to the using LTE modem. And if I now remove the rule that was there, so I enable Ethernet 0 again, eventually one of these periodic testing procedure will detect that the Ethernet 0 is working. It has lower cost, so it will switch back to using it. And eventually it will also be shown here in the Z controller as being in a working state. And now let's make an example that I configured it wrongly. I choose Ethernet 1 as management, which however cannot physically provide connectivity to the controller. And if I submit it and EOS would just assign it and not do anything with it, I would permanently lose connectivity with the device. But as you can see, I'm getting here error. And just the fact that I'm getting the error means that the connectivity is still working. And that's because the device has tested this new configuration, but it failed the test. It couldn't connect to the controller, so it fell back to the previously working configuration where Ethernet 0 and V1 was used. And in this console output somewhere there, yeah, I will see that we are not using the highest priority, not the latest network config. Yeah, that's all for this demo.
So Milan, I want to add like a couple of bits of information. First one on the cost. So we do have like from a use case perspective, we do have customers who have LTE and satellite modems that they use to connect to the devices. And when that happens, what happens is that from a device perspective, they're actually connecting to a wired Ethernet port, but that wired Ethernet port is going to a satellite modem or to an LTE on the other side. So that makes it like very, so they want to be able to configure the cost of that to be very high. Even though it is an Ethernet, they configure it to be a very high number, like let's say 100 versus 10. And then now we will be able to like manage saying that, okay, if there is a lower cost interface available, use that versus using this one. Even though they are physical Ethernet for the device, they might be connected to something more expensive on the other end. Okay, so that's the first point I wanted to make. And the second one, in terms of the network falling, and the second one in terms of the network falling back to its last known good image or last known good configuration. Some of our customers do not want that to happen. And sometimes it might be that like the far end has gone away, the net gateway has gone away, the DNS is misbehaving. So they do not want the network config to change on them. And there are ways you can use to like limit that change. So you can say, even if there is an error, then do not fall back. And that is a configuration knob that the users can use to set, saying that even if there is an error, do not fall back, wait for a manual intervention to happen, or wait for the network to resolve itself. Milan, I'm done. Sorry. Just wanted to make sure like we are clear on those 2 points. Okay.
Yeah, I hear there's some noise on Carlos Esteves line. I don't know if he hears.
Yeah, Carlos, you might want to mute your. Yeah, thanks.
Okay, thanks.
Yeah. No. Okay. Thanks. Thanks, Vijay. Right. And so now we are moving from device connectivity to application networking. So applications, they need networks to connect either between each other on the same device, or maybe with some external endpoints, either somewhere in the enterprise network or even maybe in the cloud. And in that case, maybe even VPN is needed. So for all these cases, we provide several connectivity options. One of them is a direct attachment of a network adapter or PCI pass-through. So you can basically, in this case, the network adapter is put, it's no longer used no longer used and seen by the host, and it is put into the application virtual machine. And in this case, the application has to completely manage this network adapter. It has to maybe configure the HCP client. It's all up to the application to do whatever it needs to do with the interface. But we then also provide some network instances where we give you some services, make it easier for applications. So the most commonly one used is a local network instance, which is basically an L3 network. So it is routed inside EU. It uses an IP addresses from a space separated from what is used by the device. So it is separate IP addressing, and there is a NAT in between this network instance and the device networks. And for these local network instances, EU provides several services like DNS. So there is a DNS server running inside EOS. It's actually DNS mask, which also provides a DHCP server service. As I mentioned, IP address management is provided by EOS. And because there is a NAT in between this network instance and the of device networks, it is not possible to access applications directly from outside. Applications can access obviously anything outside, but you cannot go from outside to the application because of the NAT. But there is an option to configure port forwarding through network ACLs, which I will mention shortly. Another type is switch network instance, which is basically just a bridge inside the device. It's a bridge. Application interfaces are put under this bridge, and this bridge is connected with a selected single uplink port. So this is completely like bridged inside device. It's all L2 layer. It doesn't go up to L3 inside the device. There is no routing, no NAT, no anything. And for this, we also provide VLANs. I will talk about this shortly. And then there is another type, VPN. It's still in the beta, not used very often. It is similar to local. It's also L3 with its own IP addressing, all the services. However, there is a NAT. Instead, there is a IPsec gateway. It's provided on the IKE side. It's handled by StrongSwan. So StrongSwan is an IKE daemon, and then it obtains some IPsec configuration. You have to put an IPsec configuration to this, and StrongSwan then, based on that, establishes an IPsec tunnel with some remote IPsec gateway, and you will get then a tunnel interface. And so, if whatever external connectivity will be happening, will go through this tunnel interface over the VPN. Now, as I mentioned, so these network instances, on one hand, they provide connectivity between applications on the same device, but often applications need to communicate with some external endpoints. So the network instance in that case needs to be associated with some uplink port, with some physical network adapter. And it can be a single specific uplink interface. It can even be one that is already used for management, or it can be some that will be used only for applications. If you don't care which uplink interface it will be used, then you can choose that there is like an option to put there a constant uplink, which means that any working uplink interface will be used. And EOS will be periodically testing all the uplink interfaces, and it will choose the one which is working, but at the same time it will be optimizing to choose the one with the lowest cost. If you don't need any external connectivity for your applications, you can configure network instance without uplink port, and we call that air-gapped network instance. So here I have pictures for all these different types. So this is a local network instance. This is like a virtual switch here, providing all these services. It is assigning IP addresses from some private IP address space, and then in between here there is in this case it is associated with a network adapter, physical network adapter for external connectivity. But in between here there is a routing and NAT. So you cannot access this application directly. You have to go through a port forwarding rule. And in this case, this is the same, except that there is no association with any uplink interface. So in this case, this application can communicate with each other through this network instance, but they cannot access anything outside. This is a switch network instance without those services, and that's because this is bridged, directly bridged with a selected uplink interface. And so, for example, if on this network, on this physical network, you have some DHCP server and applications ask for a IP address, they may actually get from this DHCP server IP address. And so they will be very much visible on this physical network and can be accessed directly.
So a quick question on previous slide. I think you guys do, I'm not 100% sure, but you have a mechanism to track bandwidth consumption per app, right? Like do we have visibility to the consumption of network for each app deployed?
Yeah, we have our RX takes metrics for application interfaces. If that's what you mean, I'll be actually showing it later. Yeah, and the switch network instances, they have they support VLANs. So let's say that on this physical network, there are already some VLANs to to partition the broadcast domain and to basically create a multiple networks, but virtually. If you don't use VLANs, if you don't configure them, then it will be the packets will go through application interfaces regardless of if there are tags or if there are any, and what those tags contain. But you can configure a specific VLAN number for a given application network interface, and then it will only contain, receive those packets which are tagged for that VLAN. So that application will be inside that VLAN. But also you can still put their application which is configured for any VLAN. So that means with a trunk port. And in this case, for example, let's say that these applications are split into two VLANs, but also there is some router application, and that can inside contain VLAN sub interfaces and do routing in between them. That's an example how this can be used. This is only for switch network instances, and so it's only for applications in them. It's not for the management plane yet, but there is some work in progress. And then finally, there are VPN network instances. It's very much just like the local network instance, except that instead of routing a NAT here between network instance and the network adapter, the physical network adapter, there is actually a tunnel which is connected with some remote IPC gateway, and all the packets that are routed outside will go through the tunnel. They will be encrypted, and they will go to the other side of the VPN tunnel. Here I have another example. So here, let's say that you have some applications, but you may want to apply some of your own filtering, maybe block some malicious activity. So in that case, you can deploy firewall, and you can actually deploy it as an application on the same device next to your other applications. And in this case, I decided that this network adapter will be used directly by my firewall application. That's an example. And other applications will be connected to the firewall through a switch network instance. In this case, also like separated into VLANs. Maybe you might want to have different policies for these VLANs. And the switch network instance has it's not connected with any network adapter, so it's air-gapped. And this is to enforce that all the traffic that goes out from these applications or into those applications and is between some external endpoint has to go through the firewall applications that apply some policies. Right, and the next topic to discuss is network ACLs. So for each application network interface, there is one ACL assigned to it, one access list. Access list is essentially a list of access control entries that collectively define the network traffic profile. So they basically define what is allowed to go in, then maybe some bandwidth limiting or some packet bungling, specifically port forwarding. And so as I mentioned, there is one ACL for each application downlink interface, but it may contain multiple access control entries. These access control entries, they are divided into outbound and inbound direction. Outbound, that means that this is from the application point of view. So outbound is for traffic that originates in the application and goes out towards external endpoints. And in this case, you can apply ACs, which then do some maybe filtering or bandwidth limiting. And each of these access control entries is composed of some match rules. Basically, they say both packets should be matched by that access control entry. And these match rules can be based on, for example, L3 fields like IP source, IP address, destination IP address, even host names. So if application is making a request to some external endpoint, but it is using a domain name, the DNS request will be always allowed. But if there is an AC which blocks it to access that domain, then the actual request, which has the actual IP address, that will be blocked. So the EOS, inside there is a mechanism basically that remembers for a given domain name to which IP address, the IP address and domain name association, it remembers it and then applies the rule. And on the inbound side, it is possible to have these port forwarding rules, which I mentioned. This is to be used for local network instances, to have them accessible from outside, and also you can apply limiting, so limiting the bandwidth, right? And so this ACL contains multiple ACs. There are some actually on the next slide. This is the content of a ACL, how it looks like. So there are some ACs which are automatically implicitly added there, even if you do not configure them, and they are there to permit protocols like DNS, DHCP, or the HTTP for cloud init, IPv6 network discovery. So this will be always allowed to pass. And then there are rules which you as a user configure explicitly. For these rules, the default action is to allow. So if you are talking about filtering, you actually don't have any reason to use anything else than allow. And that's because at the end of ACL, there is the implicit drop all AC. So by default, everything is denied except for these protocols, and you have to explicitly configure what you want to allow. Yeah, in more details, this is described by this document in the EVE repository. And I have a small demo here. So again, with the ZDDA commercial controller. So here, when you are creating an application, just the definition, not an instance yet, then you are actually configuring the ACLs as well. So this is a definition of my application. And here there is this section environment, and that's actually the ACLs. So there is, you configure one environment is one ACL, and you configure environment individually for each network interface of an application. In this case, I have only one network interface. So there is one environment. I have here outbound rules for filtering. I allow my application to access google.com on both HTTP and HTTPS. And actually there is a feature in EVE that this will be applied not only for google.com, but also for any of its subdomains. So also, I don't know, docs.google.com will be allowed as well. This actually cannot be disabled, so you just need to be aware of this, that this will allow, it's like there is an asterisk in front of this. Actually, we otherwise do not support wildcards, but in this case, you can imagine that there is an asterisk in front of this domain name. So these are outbound rules for filtering. I have one inbound rules to map this port and the device IP address as seen from the outside to be mapped to my application IP address and this port. So this is for me to be able to SSH into the application, and I should be able to do that. So you know, I'm SSHing in onto this port. Here you would have like a real node edge device IP address, but this is running here locally. It's a virtual machine, and using this inbound ACE, I'm able to SSH into my application. I have allowed my application to access google.com. So yeah, I'm getting some response. I will be also able to access any of subdomains, you know, even if they have a different IP address, which in this case, it is actually true. These are different IP addresses, but subdomains are automatically allowed. I will not be able to access anything else. So this will be just timeouting. Right, so these are ACLs in action. Now, about some troubleshooting. So if you have a edge node which is not working well and you are suspecting that this could be a network issue, that there are multiple places you can look into. So there are edge node events, right? They are published by EOS, and I will show them here in the commercial controller. If I go to my device, I can look under events, and some of these events may be actually related to networking. There is just one in this case. I can see that my network instance used by my application has chosen the Ethernet 0 interface, and there is no updates, so that means it's still using the Ethernet 0. Then you can look at the metrics and state data. So these are available. These are again published by EOS. And for the commercial solution, you can either look into the controller. For example, here under adapters, you can see here the all the takes RX counters. And also you can use ZCLI to show all the metrics from a given device. So I'm just going to copy the command. You can run ZCLI edge node show with raw option, and then you get everything, all the metrics, and then the name of your device. I'm already logged into the cloud, so I already run the ZCLI configure. And after a while, I'm going to get all these details. Some of these are related to networking. Let's say, for example, I'm going to show you that there is let's say that my LTE modem isn't working. I can list the metrics and see that RSSE is actually good. So the signal is good. So here I already know that the signal strength is not an issue. There might be some other issue. So these are metrics, and then the EOS is logging all the connections between applications, between themselves, and also between applications and external endpoints. A flow is essentially a tuple, so containing like a source destination IP address, source destination port, and it also contains a ID of a access control entry. This is something that you cannot see in the Z control, but when you are creating a access control list, then each of these access control entries is actually assigned a ID, unique ID. For example, the deny all default rule, which is at the end, is assigned 0, and non-zero values are assigned to those which are configured explicitly. And you can see this flow, these locked flows under reports. Here I choose network, traffic, edge instance, and I will choose my application, the one where I was just logged in, and I would try to access Google and GitHub. And yeah, actually you can see that there are 3 connections that I made. And here, this column is an AC ID. And yeah, in this case, okay. So in this case, it's actually the number 1 is used by the rule that it was dropping the connections. So these were the connections. Oh no, sorry. This one was the one that was allowing connections. So this was the access to Google, and this one. Oh no. Oh, okay. Never mind. So here we cannot see the one which was dropped for some reason, but normally we can see here not only those flows that were allowed, but also those that were dropped. But for some reason, currently it's not listing the flow that was dropped. Maybe I killed it too soon. And finally, you can, if you are on the location and the device has some potentially network issues, you can look at the LED and see at the pattern of blinking. So if it is blinking, it will be blinking repeatedly. If it is blinking just once in every iteration, it means that it's still waiting for an IP address from the HTTP server. And if it is blinking twice in each iteration, it means that it has IP address, but it is not yet connected to the controller. And if it will be blinking more times in each iteration, that means that it has connectivity to the controller, and in that case, probably not a network issue. Okay, and finally, some best practices for network configuration. One which I have already mentioned is to make sure to properly configure uplink network interface usage. So, I mean, there is this fallback mechanism. So if you configure it wrongly, then it will fall back. But eventually try to put the right correct configuration, make sure that interfaces which are marked for management can physically provide connectivity with the controller, because if not, then these interfaces will be tested periodically, and it will be just always returning failures, some delays, and they will be just delaying this whole testing process. And then maybe, so if you have management interfaces which are basically equivalent in terms of cost, then assign them an equal cost, because then you will get this load spreading feature. If you have two Ethernet interfaces and you put 0 to one of them, 1 to the other one, even though they're equivalent, then you will not have this load spreading functionality. And then also the last resort network configuration, it's maybe something that is not so recommended to be used in production. So prefer to disable it, maybe provide the right configuration through USB stick as an initial configuration. Yeah, and I have one more slide. This is specifically for the commercial controller. And the reason for that is, on the Eve OS side, the whole device configuration is basically one big JSON configuration, including the network configuration. But in that control, the things in the UI are split into multiple pieces. And if you are struggling to find what is configured where, then this should give you some overview. So firstly, let's go from the bottom up. So you are configuring networks. So these are like the physical networks to which your device is connected. You are configuring this under a library tab. And then you are creating your edge node. When you are creating your edge node, you are using a model from the marketplace, which was edited using ZCLI. And under the edge node, this model gives you a list of edge node adapters. And when you are creating the edge node, you are putting the edge node adapters into corresponding networks to which they are connected. Now, when you have this, you have basically your prepared configuration for your device. But now going up to the applications, now you will be creating network instances under library. And for each of them, you will choose you will associate every network instance with the edge node. And from a list of edge node adapters, you will choose one as an uplink, or you will select the uplink constant, saying that basically you don't care which adapter is used as uplink. So this is done in the library. And then in the library, you will also have the application image created. You will create it there. And from there, you will be creating application definition in the marketplace, where you will define these environments, or ACLs essentially. And then you will be creating an application instance. You will be assigning each environment to a network instance, and you can also configure VLAN right there. So, in the UI, all this big network configuration is split into multiple pieces, but eventually it is sent all as one into the OVS to apply. Right, and finally, I can just announce some current work that is planned for future. We would like to give you IPv6 support. This is a work in progress. Also, we would like to extend the VLAN support, maybe with some bonds and lags, and not only for applications, but also for the Eve management traffic and local network instances. And another thing is being worked on is to properly isolate network instances using VRFs, because currently it is not possible, for example, to create two local instances with the same IP subnet, even though semantically these network instances should be completely separated, isolated from each other. Currently, this is not isolated. The routing would not work. EVOS would not allow you to deploy this. So we are planning to basically isolate them using VRFs. And then also something that we are thinking about is to provide some high performance packet processing options for network function virtual and container network functions applications. So basically for applications that need high performance networking. I mean, one option is that you use the direct assignment of network adapter, and then you can do whatever you want with that network adapter. But also we are considering whether it would make sense to have a support for something like DPDK or SRIOV inside EOS. And that's all from my side. So now it's time for questions. Thank you.
So the VPN settings that you showed earlier that are in beta, what do you have a time frame on that and how that's going?
Well, I guess it depends on demand, I would say. Maybe Eric will have some more comments on this, but up until now, it wasn't really that much required as far as I know. And so there wasn't like, any input on this and any need to work on this further. So we are kind of uncertain, whether we want to, have that in EOS or maybe just leave it to applications, because the application itself can open an IPsec tunnel if it needs to, or whether we really want to have this in EOS if it is actually needed that much.
So with that in mind, and yeah, I agree, an application can open up its own, but with the capabilities of the uplinks and, having multiple uplinks, I mean, I can see where if Eve was handling the VPN tunnel, I'm guessing, I haven't looked into it, but I'm guessing that it could switch which WAN or uplink connection it's using to provide more or less seamless VPN access across multiple links. Is that a fair statement?
Mm-hmm. Yeah, that's correct.
Yeah, I think so. I don't know if we actually tested that, if we've exercised that stuff, but yeah, I mean, in principle, it does, right? So.
Okay, thank you.
Rick, it was.
And the other motivation for this stuff was also sort of defense in depth from a security perspective, right? That even if your application is somehow compromised, it can't escape outside of this VPN, right? If the VPN only goes to your data center or to your AWS Azure VPC, right? It could still only go there, right? So it's a way of, in essence, extending the sandbox from the data center or the cloud into the edge. And as Milan said, yeah, we haven't seen, people that actually want to deploy this into production, which is why it's still in beta. Right?
Thank you.
So do you guys see any interest in actually, deploying this stuff in some particular environment, or?
So I can definitely see where both the VLAN capabilities and the VPN capabilities would be useful, and potentially a better design than what we have. I do know that the VLANs would be very useful, actually. Especially with the management, just to have that flexibility to create different virtual NICs to present to the edge app instance, and that way the actual virtual machine doesn't have to worry about trunking, and I don't have to worry about a switch port or a switch instance. So having more robust VLANing capabilities so that I can control that traffic before I hand it to the edge app instance would be very useful.
Okay. Yeah, I mean, if you guys have something in terms of this is the type of VLAN config you would like to see, we can actually check that matches some of the ongoing work, right? I mean, as Milan said, we have some basic access VLAN support already, for switch network instances, but we're adding more VLAN support. So.
And Eric and Rick and everyone else on the team, just a reminder that this is an LF-Edge related discussion. Let's please keep it very generic. If needed, we can always have more specific discussions around this topic.
Yeah, so just a quick one on your roadmap. Is there any intention to add more SD-WAN-ish capabilities, especially around maybe things like throttling, limiting network consumption of a particular application to prevent it from taking over the whole pipe, right? Is that something that you're considering, or it's really out of scope for you there?
So maybe I can try to respond to that. I mean, we do have, in terms of the ACL support, there is actually the ability to specify rate limits, token bucket filter, right? And, I don't know if that's sufficient or whether you actually need more. I mean, this is basically being able to specify, token bucket with a burst size and a rate, basically, right?
Sorry, I'm not sure I didn't hear your voice was kind of tapering.
Okay.
I'm not sure.
Oh, so it's basic. I don't know. The underlying implementation is something known as a token bucket, where you specify burst size and then rate, and that's been in Eve for years, right? So you specify that as part of the ACLs themselves. So you can say I can go to www.google.com with these rate limits. And I don't know if that's sufficient. I mean, it's a very basic mechanism, but you can at least prevent it from taking over the world. But it doesn't know anything about what's the actual speed of my uplink, right? You would have to know that externally to say, this guy is going to get, 1 megabit per second. Well, how fast is your actual uplink? Well, who knows, right? So if there's specific things, because the typical end-to-end solutions that do this, they can actually have a notion of actually measuring what actual bandwidth they see, and hence they can be a lot more smarter because they know who they're talking to at the other end. So they can be a lot smarter about allocating those resources based on whatever policies they have.
I was talking of instances, scenarios where you have, let's say, there could be 3 nodes or 3 apps running, right? And I might want to make sure that, I have a main app, which I want to make sure always gets, access, and so I want to make sure that maybe the third app, which is less important to me, but might start, pumping a lot of, might take over the network. Is there a way to limit, to ensure that?
It's actually very hard for Eve to do that, because Eve is typically not where the bottleneck link is, right? I mean, the only case it is if it's actually, you're going through an Ethernet or an LTE modem, and it's that 10 megabit Ethernet or whatever speed you get out of LTE that is the bottleneck, right? Only then will Eve actually see that packets are being queued or dropped. But if you're going over, like for instance, over an Ethernet to a satellite modem, well, it's the satellite modem that's going to queue or drop these packets. So Eve has no visibility into, am I pushing more things down the pipe than what fits, right? So that's the challenge in doing an Eve only solution, as opposed to something that is end to end, that's talking to something, and you actually are doing measurement to understand what is getting through and what's not, right? So sort of like an overlay network, SD-WAN type solution, typically does those end-to-end measurements to have a better idea about what's happening, and Eve itself can't do that. So it depends a bit on the use case, but I mean, there are things one can do, but it requires more configuration, and we've stayed away from this because it's sort of like, you need a PhD in network configuration. Like Eve could potentially mark things. There's something in the industry called differentiated services, where you put different 6-bit values in the packet, saying, hey, this thing should be in this traffic class. And Eve can put, we could add, in theory, add that stuff to Eve, but now you have to configure the router sitting at that, for instance, satellite link to say, okay, if I'm out of capacity, I'm going to drop things with these marks before I drop things with that mark, right? So it's sort of, Eve itself doesn't solve it. It's just providing some marking that you have to, someone would have to have the expertise to go configure that elsewhere. So.
Well, kind of take off on that question, Eric, or that comment is, do you guys look at the markings and retain them? So like if we got an internal device that's marking the traffic before passing it on, will you retain that marking or do you clear it?
So today we're not touching the DHCP code points at all, right? So.
Okay, so you pass them through then?
Yes.
Okay. And I do have another question is, what was your thought around switches and only having a single port, physical port that could be attached into a switch?
Well, so the motivation for this is that if you have a switch and you connect multiple external ports to it, you can potentially create loops at layer 2, meaning that now you need to figure out, am I going to run spanning tree protocol, rapid spanning tree protocol, BPDU guard, whatever, right, to prevent me from actually getting loops that will melt the network.
Okay, so you don't run anything like that, and therefore that would be bad.
Right.
Yeah. Okay.
Yeah, and and it's not that it's not a solvable problem. It's just that there's so many different flavors of how you actually do this stuff, right? I think that today, I don't even know what the default is if you're buying an Ethernet switch from one of the big networking vendors. If it assumes that you have a PhD in configuring those things and you figure out what you're supposed to do, or whether BPDU guard is the default and whatever, I don't actually know. But it is possible. I mean, other things that we have talked about, like, okay, we could do link aggregation, right? If you have, and what is actually sitting on that different side of link aggregation, right? Link aggregation in network parlance, NIC bonding and Linux parlance, right? That's another thing that's a potential, but we haven't had anybody said, okay, here's the actual how we would want to deploy this stuff. And, there's a number of different networking features that we haven't seen show up at these edge devices yet.
Maybe that's that might be a good question for you too. Is what is your average model? Do you see models with a lot of Ethernet in them, or is maybe there's only 2 or 3 Ethernet interfaces on most of your models?
Do you want me to take that, Eric?
Yeah.
So most of I would say we see models that fall into 3 separate buckets, at a very high level. At the bottom end are things that have 1 or 2 Ethernet interfaces maximum, and they might actually have an LTE or a Wi-Fi interface, and that's about it. But these devices are very rich in other I/O, which can be serial, all different kinds of other I/O that you can think of, right? These are used mostly at the very far end, far edge, if I may use that word, where they're directly talking to the PLCs or sensors and things like that. Then we have things that we see in the second bucket, where they still have PLCs and everything else that they don't want to talk to, but they have 3 or 4 different Ethernet interfaces of different flavors, again, like Wi-Fi, LTE, all of them combined, 3 or 4. And then the last one, which is not very common, is the where there we have devices that have 8 Ethernet interfaces or 10 Ethernet interfaces, and these are used mainly when there are use cases which have network functions that are being virtualized inside that particular device. So I would say most of the things 90 and above 90% fall into the first 2 models, where there are 4 to 6 maximum, and then anything more is we have seen them, but those are rare.
Okay.
Yeah, I mean, I guess there's nothing in Eve to sort of prevent running on those, right? If you have a box with, you know, a couple of 40 gig or 100 gigabit optical Ethernet interfaces, well, you can assign those things directly to an app instances running, right, with PCI pass-through, and you know, but we haven't actually seen that stuff out in terms of people wanting to deploy things that way. So.
Yeah, I was just thinking more along the lines of using multiple ports into a switch, not so much to connect to external networks, but connect multiple devices so that they kind of exist within the same switch domain, so to speak. But you guys kind of flipped it around. You're thinking of, okay, I've got multiple internal systems that might connect to an external physical switch, so to speak, and therefore only using a single switch port is more or safer than trying to do multiple switch ports.
Yeah, I mean, I think there's some deployments where it's, you know, you might have sort of a factory floor type network, and you have an internet facing one, and you might have some sort of DMC type thing sitting in between or whatever, or some ports that are connected solely for the purposes of deploying an intrusion detection system on Eve, right? That's just sort of sniffing traffic on some ports, right? So there are use cases when you end up using, you know, 3 or 4 that are of very different types from sort of a security domain perspective. Right? So there's a fair bit of variation, and we haven't run into cases where Eve can actually support this stuff, right?
It's probably just time on your side to make sure it works, right?
Yeah, and some of that is more about the applications, right? I mean, so some of the things we didn't touch upon here, but when you go and deploy virtual network functions, right? Well, they might make assumptions about how are they, if they have, you know, 3 Ethernet interfaces, but how are they actually enumerated, right? If I'm booting this thing, what is actually Ethernet 0 as seen by that application instance? Well, that might be a function of the hypervisor and the BIOS that you're using to boot the guest VM and a bunch of other things, right? So that's a bit of you know, rocket science in terms of figuring out, well, how will these things actually appear, right? So it's something that that type of thing actually requires some testing to make sure that, you know, if it's an app that has a single Ethernet interface, well, that always works, right? But if it has 3 of them and one of them is direct assignment and 2 of them are virtual ones, well, which order do they actually appear as seen by the app, or how does the app instance name them? And if this is now not a Linux or Windows, but it's a DNF that's, you know, a networking vendor that has built this thing, well, you know, how did they actually do the enumeration down in their kernel or whatever? And there's a fair bit of variation there.